Hello and welcome. Today we are excited to introduce an impressive NVMe solution based on PetaLinux, capable of delivering 7,000 MB per sec data transfers.
That's right, by using our NVMe Gen4 soft IP core, combined with advanced techniques such as a dual-channel DMA engine with coherent memory, we can efficiently transfer data between main memory and NVMe SSD, reaching full bandwidth of PCIe Gen4 7,000 MB per sec.
In this video, we will walk you through the key techniques behind our solution and show you a live demo of it in action. Let's get started. There are many types of applications that need high-speed access to NVMe storage. So, the system we use is based on embedded Linux on FPGA, working together with an NVMe SSD. In most cases, the system runs on an FPGA with PCIe hard IP and PetaLinux, which takes care of the NVMe SSD through its driver. The performance we achieve with the system is around 2000 MB per sec when accessing an NVMe Gen4 SSD. But this 2000 MB per sec is not the maximum speed that the PCIe Gen4 hard IP can handle. Because we have to use PetaLinux, there is software overhead, which makes the performance lower than the full bandwidth. Another issue with this system is that not every FPGA has a PCIe hard IP, which limits the flexibility in choosing the device. But we will show you that we have overcome these limitations. By using our own NVMe Gen4 soft IP from design gateway, integrating it to the FPGA, and using the NVMe driver we developed ourselves, designed to work smoothly with the NVMe Gen4 soft IP. Plus, our solution works with any FPGA. With our solution, we were able to push the performance to 7,000 MB per sec, which is the highest performance ever achieved on this type of system. The main advantage of our solution is that it can boost performance by 3.5 times compared to the previous system, while offloading all CPU tasks from software to hardware and using advanced dual DMA engine. Next, we will talk about the key point of our design. From here, I'll hand it over to our FPGA engineer to explain more.
Now, let's take a deep dive and explore the details together. Let's go over the details of our hardware design. Our hardware design mainly features the dropping of the 128-bit data port to 2 ports, which increases the bandwidth by 2 times for both memory read and write access. Additionally, we have a data alignment section to correctly arrange the data from both data ports. We also need software to ensure the system works properly with our hardware. This is our custom software driver, optimized to work smoothly with our hardware. The workflow is as follows. When a user issues a command, the application makes a system call to the driver, which then forwards the request. The actual transmission control is offloaded to our hardware, ensuring maximum performance and efficiency. The main feature of our driver include lower CPU resource usage. When used with the NVMe Gen4 soft IP from design gateway, it sends a request just once without needing to split the data into multiple parts. It also reduces the software overhead, which is the main issue of affecting performance. From everything we have covered, our system has completely transformed, enabling us to use an NVMe Gen4 SSD with write and read performance of around 6,900 MB per sec and 7,500 MB per sec respectively. Now, we will walk you through a live demo starting from the FPGA board setup and moving on to running an application for basic system testing. Let's begin. To set up the hardware, start by connecting the NVMe SSD installed in the Drive 1 M.2 slot on the AB17 adapter to the HPC connector on the FPGA board. Then insert the SD card preloaded with PetaLinux boot image file into the SD card socket. Use a micro USB cable to connect the serial console to your PC. Finally, connect the AMD power adapter and power on the FPGA board. After successfully booting the PetaLinux system on the FPGA board, we will demonstrate running the DG NVMe command to show the write and read performance, as well as to perform a hex dump of the data from the SSD. First, we run a write performance test, measuring how quickly data can be written to the NVMe Gen4 SSD. Next, we perform a read performance test to evaluate the read speed from the SSD. Finally, we use the DG NVMe command to perform a hex dump, displaying the actual data stored on the SSD in a raw hexadecimal format. This command displays data in 4 KB segments and pressing N load the next segment for sequential reading. After showing the demo result, we can conclude that we successfully built a high-speed NVMe system on FPGA using our own NVMe Gen4 soft IP and custom NVMe driver.
This solution works on any FPGA, removes CPU bottlenecks, and boosts performance up to 7000 MB per second. That's 3.5 times faster than the old setup. Thanks for watching, and we hope this inspires more innovation in high-performance FPGA storage systems.